Hello and welcome to Unit 7. This is Mr. Boothman, and Unit 7 is Analytic Trigonometry. This is by far my favorite unit this entire year. Section 7.1 and 7.2 are by far my favorite sections this entire year. I've been waiting to teach this for months. You don't understand how excited I am. I love trig identities. These are the greatest thing ever, in my opinion, and I really hope some of you are enjoying these at least partially as much as I do. Let's talk about what those are. So 7.1 is all about using the fundamental trig identities. We've actually talked about these identities before. An identity is another way of talking about a value in math. It's another identity of that value. Haha. And we've already done this to some extent. We see the reciprocal identities in here. And those are all the definitions of sine and cosine and secant and cosecant and tangent and cotangent. Those are the definitions we've talked about before. If I've asked you to calculate the cosecant of an angle in your calculator, you know that you do 1 divided by the sine of that angle. That's literally just the reciprocal identity. The quotient identities come from the definition of sine and cosine. So reciprocal identities, this was just from definitions. The quotient identities here, we know that tangent of theta is y over x. That's from Unit 5. Well, y, we know, is equal to the sine value, and x is equal to the cosine value. So the quotient identity says that tangent of this angle equals sine divided by cosine, which is right there. Cotangent then is the reciprocal of tangent, so I just flip it. Cotangent is cosine over sine. The Pythagorean identities are probably our most used identities for the purposes of what we're doing this unit, but they're also really interesting. So if I have an angle on the unit circle, there's my angle there. If it's on the unit circle, the hypotenuse of this triangle is 1. This value right here is x, and this value is my y value. But we just said y is sine of theta, x is cosine of theta. Again, that's from Unit 5. And this is a right triangle that we just drew, which means that we can apply the Pythagorean theorem. So the Pythagorean theorem would tell me cosine squared plus sine squared equals 1 squared. And usually we write this as cosine squared of theta plus sine squared of theta equals 1. That's just how we write this. That's our notation for it. Putting the exponent right next to the function in there is a shorter way of writing this without having to draw the parentheses each time. Note that this is not the same as saying sine of theta squared. Theta squared is squaring the angle. It's totally different. So these are not the same thing at all. And so right here you see our Pythagorean identity. Sine squared plus cosine squared equals 1. If I divide each term here by cosine squared, for example, and simplify it, then I have 1 plus sine squared over cosine squared is tangent squared. 1 over cosine squared would be secant squared from the quotient and reciprocal identities, respectively. And that's my second Pythagorean identity. If I divided each of those terms in the first identity by sine squared, then I would get 1 plus cotangent squared equals cosecant squared. So that's where those identities are coming from. Also, when I'm talking and as I'm explaining, I will often abbreviate sine squared of theta to just sine squared. I'll say sine squared plus cosine squared equals 1, rather than sine squared of theta plus cosine squared of theta equals 1. Now, I hope you do realize that's just me trying to be a little more brief. However, those are still the same thing. Like, theta is still there. The angle measure is still there. This is a function, after all. This is just an easier way for me to have to talk about this. Okay? The cofunction identities right here, they really just come from where the angles are on the unit circle and how these angles end up relating to one another. We could go through an example for the first one at least. So if I say theta is pi, then the cofunction identities would tell me that this statement is true. Sine of pi over 2 minus pi equals the cosine of pi. So this would be the sine of negative pi over 2 equals the cosine of pi. And sine of negative pi over 2 is negative 1. Cosine of pi is negative 1. So that's true. So the cofunction identities are really just ways of relating the function values around the unit circle based on their spacing. We don't use them very much, to be perfectly honest. I don't think I've ever used the cofunction identities, but they are useful in some situations, and they're true facts. So they're there if we ever need to use them. Finally, the even and odd identities. We've seen the words even and odd before, all the way back in Unit 1 in the fall. The even and odd, we talked about in terms of functions. Functions could be even or odd. If you remember, even functions were symmetric with respect to the y-axis. Algebraically, that meant f of x equals f of negative x. Now, we did touch on this back in Unit 5, but if we look at the graph of the cosine function, that is the graph of the cosine function. I do apologize. We see that this is symmetric with respect to the y-axis. And if we test it algebraically like this, we see that, indeed, cosine of an angle is equal to cosine of the negative angle. So that's where we're getting that identity up there. Odd functions were a little different. Odd functions are symmetric with respect to the origin. Algebraically, that means negative f of x equals f of negative x. And if we look at the sine graph, it is symmetric with respect to the origin, and algebraically this works out too, which is where we're getting this. And so we could go on and on for the other trig functions. But basically, these are called even and odd identities because they stem from the fact that the trig functions are even or odd functions. Okay. One last note about manipulating these identities before we actually start using them. We will often use other forms of the Pythagorean identity, and all I mean by that is that you might take sine squared plus cosine squared equals 1, and you can move things around in there. It's algebra. So subtract sine squared from both sides of this, and you'll get cosine squared of theta equals 1 minus sine squared of theta. Okay? And you can do the same for the other two identities. You could subtract cosine squared from both sides. Things like that. So just being able to recognize that we can manipulate these identities algebraically, that's totally fine, as long as we use proper algebra. So how do we use all of this is a natural question. I'm going to start with kind of an edge case where it's something we can do with this, but it's probably not something I would ask you to do with this, and that is to evaluate trig functions using the fundamental identities. So you'll recognize the setup of this first example. It's kind of setup that we've seen before. We know how to solve this in another way, but this time I want to solve this using the trig identities. So we look at our formula sheet, and you are given your formula sheet. You do not have to memorize all of those. Lucky you. I had to memorize them in high school, but anyway. Look at your formula sheet and try to see which formula or which identity relates secant and tangent. And you'll see quite quickly that it is going to be the Pythagorean identity right here. 1 plus tangent squared, we're using u in this case, tangent squared of u equals secant squared u. And they told us what secant squared equals, so 1 plus tangent squared u equals negative 3 over 2 squared. Tangent squared u equals 9 over 4 minus 1. So tangent squared u equals 5 over 4. Take the square root of both sides, and you'll get tangent equals plus or minus the square root of 5 over 4. And if I keep simplifying this, I will get the square root of 5 over 2. Tangent is positive, it tells me. So that means my signs could either both be positive, top and bottom, or they're both negative. And I see that secant is negative, which means that I'm going to go with these negative values here. If you'll recall, tangent is y over x. And for these kinds of problems, I'm looking for r, x, and y. So x is negative 2, y is negative square root of 5. We can find r using the Pythagorean theorem. R squared equals x squared plus y squared. Simplify that, we will get the square root of 9, which is 3. And so from here, we can set up the rest of our answers. Sine of u is going to be y over r, or the negative square root of 5 over 3. Cosine of u is going to be negative 2 over 3. Tangent of u, square root of 5 over 2, and so on. The other three functions being the reciprocals of these three functions. So we could do this. I think it's more work than just solving this kind of problem the way that we've learned how, but this is possible. Kind of interesting. A curiosity, if nothing else. The main reason we use these identities will be clearer in section 7.2, but for section 7.1, we use these identities to simplify expressions. Basically, we're going to take an expression that looks like this, a really long expression, a bunch of different functions. It looks really complicated, and we're going to use our fundamental identities to simplify it. We're going to plug things in and turn it into something that's easier for us to work with. So example 2, sine of x times the cosine squared of x minus sine of x. Next to each of these problems, I'm going to write what I'm thinking when I see this problem and how I'm going to go about simplifying this, and what I hope you'll eventually learn to be able to see yourself. So right away, I see this problem. I see cosine squared of x, and anytime you see a term that's squared, cosine squared, secant squared, tangent squared, cosine squared, sine squared, what's the only one that I didn't just list? Cosecant squared. You're going to think Pythagorean identities. So if we look at the Pythagorean identities, you'll remember that sine squared plus cosine squared equals 1. If I solve that for cosine squared equals 1 minus sine squared. And I'm going to substitute. I have cosine squared here, and I have cosine squared up here. I can substitute in for that value. So sine of x times 1 minus sine squared of x minus sine of x. All I did was substitute right here. And now I can distribute. Sine of x times 1 is sine of x. Sine of x times negative sine squared of x is minus sine cubed of x. If that throws you off, then think of this as what's x times x squared. That's x cubed. Sine of x, it's the same thing. It's a function. It's a value. So I'm just squaring it and then multiplying to get sine cubed minus sine of x. So I'm jumping from there to here, and now I'm continuing. Does anything cancel? I see sine of x minus sine of x. That goes away. So I'm left with negative sine cubed of x. And I would be perfectly content stopping there. I believe that that is a much simpler expression than what we started with. We started with 3 values. We started with sine, cosine squared. We were subtracting. Now I'm left with 1 term. It's definitely simpler, and it's definitely easier for me to work with. Okay, moving on. Cotangent of x times secant of x. Now what I'm thinking right away, I see cotangent. This is true if I see secant, cosecant, even tangent sometimes. I'm going to change to everything being in terms of sine of x and cosine of x. because that'll really let me cancel things out more easily. It'll let me add and subtract things more easily. It's just going to allow me to perform algebra more simply to get this expression to be more manageable. So I'm going to change cotangent of x, secant of x, to something in terms of sine and cosine. So I'm going to look at my identities. I see from the quotient identity that cotangent of x is equal to cosine of x over sine of x. And I know from the reciprocal identities that secant of x is the same as 1 over cosine of x. I'm still multiplying these two terms, like I was in the given expression. And now I see right away that cosine of x cancels out. It's in the numerator and the denominator, it's going to go away. Which means I'm left with 1 over the sine of x. And from the reciprocal identities, we know that 1 over the sine of x equals cosecant of x. And that's it. I just love these problems. We took something that was more complicated and made it more simple. So much of our goal in mathematics, especially when you get to much higher mathematics, is to simplify and find something that's more elegant and easier to use. It's truly about the beauty of mathematics, I think, is why I love this section so much. But I digress. I apologize, most of you don't care about my ridiculous obsession with this, but I hope some of you do. For example 4, I see the same thing. I see cotangent, secant, cosecant, tangent. I'm going to change it to sine and cosine. So this equals 1 over the cosine of x, all over cosine of x over sine of x, plus tangent is sine over cosine. And now I'm going to just do the operations that it's telling me to do. I'm going to add the two fractions in the denominator of this whole expression, 1 over cosine of x, all over. My common denominator down here is going to be sine of x times the cosine of x. So I need to multiply this by cosine of x, top and bottom. I can't just do it to the denominator. I'm going to multiply this fraction by sine of x over the sine of x, and simplify that, multiply it, add them because I'll have the same denominator, sine of x times the cosine of x, and I'll have cosine squared of x plus sine squared of x. Next step, I see that cosine squared plus sine squared, I told you, I immediately think Pythagorean identity. I recognize that that is the same as 1. Okay? And now, I see I can divide. This fraction bar right here is telling me to divide. And when I divide two fractions, that is the same as multiplying by the reciprocal of the second fraction. We see again that cosine of x cancels, and I'm left with just sine of x. It's so elegant. There's no other word I can think of to describe this than elegant, and I truly love that so much. Let's look at example 5. Again, I see cotangent. I'm going to change that to sine cosine. So sine of t plus cosine of t over sine of t times cosine of t. I cannot cancel anything out here. Okay, I'm adding. I can't cancel across that addition. Cosine and cosine are both in the numerator, so I'm just going to do what this is telling me to do. Sine of t, and that's to multiply. Cosine times cosine is cosine squared of t over sine of t. And again, now I'm going to get a common denominator. I'm adding these two terms, and one of them is a fraction, which means I need a common denominator. That's going to be sine of t. What I do to the denominator, I need to do to the numerator, because you'll see that this is really multiplying by 1. I'm not changing the expression's value. I'm just changing the way it looks. And when I simplify this, I get sine times sine is sine squared of t. And I'll have two denominators that are both sine, so I can add the numerators. And that's what I get. And sine squared plus cosine squared is 1 over sine of t, which is cosecant. I don't know why I just wrote x. cosecant. It's so incredible. It's just beautiful. What I truly hope and encourage you to do when you're doing problems like this is to not think of these as math problems. Don't approach this and say, look at all of this algebra, look at all of this trig, look at these weird looking expressions and exponents and fractions. Think of this as a puzzle. It's a logic puzzle. You're given all the tools that you need to simplify these. It's just up to you to see what you can fit into this. What can you change? How can you rewrite this? And what cancels out and simplifies? It's a logic puzzle. Truly, think of it in that way, and I guarantee that you won't dislike this. You might not love it as I do, but you certainly won't hate it. All right, example 6. I'm going to go through example 6 after I look at examples 7 and 8. So examples 7 and 8 are all about one of the methods, one of the techniques that we use while we're simplifying these expressions. And that is to recognize that when I look at the Pythagorean identities, I see that they deal with terms that are squared, which often means that I'm able to factor some of these expressions. Case in point, right here, secant squared of t minus 1, you should look at this and think this is the difference of squares, which means I can factor difference of squares, if you've forgotten, x squared minus y squared. That factors to x minus y times x plus y. This is no different right here. Secant squared minus 1, which itself is 1 squared. So this is going to be secant minus 1 times secant plus 1. And that's my only point here in example 7. That's all I wanted you to recognize, is that you can factor some of these and to start recognizing difference of squares far more often, because too often many of you do not. Example 8, another way of thinking about factoring: when my leading coefficient is not 1, immediately I recognize that I need to factor by grouping. Factoring by grouping means if I want to use this X tool to organize my thinking, I need to multiply A and C, that's negative 12, and then B goes on the bottom. I need two numbers here that multiply to negative 12 and add to positive 1, and I know that's 4 and negative 3. So if I use those numbers, I can split my middle term. This is going to be the same as 4 tangent squared plus 4 tangent minus 3 tangent minus 3. You'll notice that all I did was take this plus 1 tangent, and I used these two numbers I got here from my x to split that term, to rewrite it. 4 tangent minus 3 tangent is still plus 1 tangent. I haven't actually changed any value. But now I can factor something. I can factor a common term out of these first two terms. I can factor out a 4 tangent. That leaves tangent plus 1 from these first two terms. From the second two terms, I can factor out minus 3, and that leaves tangent plus 1. And now I can factor out this tangent plus 1. And this is what I'm left with. Okay. So again, that was my only goal, is to refresh your memory with these other techniques we can use to factor things. And with that in mind, let's return to example 6. I love example 6. We said that we could rewrite the Pythagorean identity in terms of cosine squared, or equaling cosine squared. Cosine squared equals 1 minus sine squared. And now I hope that you recognize 1 minus sine squared is a difference of squares itself. I can factor that. 1 minus sine theta times 1 plus sine theta equals cosine squared. So for example 6, I see this denominator here, 1 plus sine theta, and what I am thinking is that 1 plus sine theta is a factor of 1 minus sine squared theta, the Pythagorean identity. We like the Pythagorean identities a lot when we're doing this because they often allow us to simplify very nicely. 1 minus sine squared is cosine squared. Sine squared plus cosine squared is 1. Things will cancel out really nicely. And so I see this and I recognize that 1 plus sine theta is one of these factors. I want to force the Pythagorean identity to appear. I want to make this into the Pythagorean identity to make this easier for myself. So how can I make 1 plus sine theta turn into 1 minus sine squared theta? I can multiply by the other factor, 1 minus sine theta. And so if I multiply 1 minus sine theta on the bottom, I'll need to do the same up here. And so I'll have 1 minus sine theta times cosine theta in the numerator. In the denominator, I have 1 minus sine theta times 1 plus sine theta. That's this right here, which equals 1 minus sine squared theta, plus the other term here, 1 plus sine theta over cosine theta. And now, 1 minus sine theta times cosine theta. I know in the denominator I have 1 minus sine squared theta. That is the Pythagorean identity. That will be the same as cosine squared theta. And I hope you'll notice that we can cancel a cosine there. 1 minus sine theta over cosine theta plus 1 plus sine theta over cosine theta. I have two fractions. I need to add them. Happily, I already have the same denominator. So 1 minus sine theta plus 1 plus sine theta all over cosine theta. In the numerator here, minus sine theta plus sine theta cancels out. 1 plus 1 is 2 over cosine theta. And for simplicity's sake, or for clarity so you can see more clearly, if I factor out that 2, just rewrite it. I have 2 times 1 over cosine theta. 1 over cosine theta is secant. So this whole expression simplifies to 2 times the secant of theta. That's incredible to me. I just can't get over how truly elegant this is. It's beautiful. Anyway, that's it for section 7.1. So there's plenty of practice problems posted, a ton of practice problems, because the best way for you to get comfortable with this is just to try this yourself. View these as puzzles, approach these as puzzles, and I promise this actually becomes pretty fun. If you have questions, please bring them to me. Otherwise, I'll see you in section 7.2. Thank you so much.